Hello and welcome back to class. In this lesson, we are looking at circle theorems, the second part of that lesson that we started some time ago. Our objectives for this class are to discover and state theorems for cyclic quadrilaterals and to discover and state the theorems related to tangents and circles. Quite a little bit of stuff there needed to be done, so we're going to jump right into it. Of course, we're going to do a little bit of questions here and there to cement some of that understanding. But this lesson really is to demonstrate what the theorems are and to show you how they work. Perhaps in another lesson, we can look at how to answer some of those CXC questions which are not featured in this video. So our first thing here is to look at cyclic quadrilaterals. What exactly is a cyclic quadrilateral? Well, a quadrilateral is a four-sided shape, a four-sided polygon, and to be cyclic, it needs its vertices on a circle. So any shape for that matter that has its vertices on the circumference of a circle is called cyclic. So here our cyclic quadrilateral is a quadrilateral with its vertices A, B, C, D on the circumference of the circle. And there are two theorems that are associated with cyclic quadrilaterals. The first one is that opposite angles in a cyclic quadrilateral are supplementary, meaning that they add to 180. So any pair of opposite angles, such as B here and D, they're opposite to each other in that sense. So they would add to give you 180 degrees. Likewise, A and C are supplementary to each other because they're opposite. So they would add to give you 180 degrees. That's the first theorem. The second theorem is if we should draw a line such as BC and extend it to create the angle DCE, that's this angle here, then this angle that is drawn on the outside, the exterior angle here, would be equal to the internal opposite angle. That is this angle that is drawn on this side of the diagram. So whatever size this angle is going to be the same as this angle. There are many good reasons for that, but we're not going to go through it right now. Also, if you wanted to look at another side, for example, say you wanted to extend this line, and you extended this line here and form this angle. Let's say you form this angle here. Then this angle in its size is going to be the same as the angle that is interior opposite to it. So that's what we mean by the second theorem. So the first theorem is that opposite angles in a cyclic quadrilateral are equal. That is, when you look at opposite angles in terms of angles being across from each other, these two are equal to these two are supplementary. Did I say equal? Opposite angles are supplementary, and the external angle formed, they're equal to each other. Now let's demonstrate that and see how it works on the actual diagram. So here we're going to draw a circle, and let's draw that circle and put a quadrilateral inside of that circle. So let's put a quadrilateral. Any random quadrilateral will do. Here we go. And so here we are. And so we have our four sides. And now these two angles should be, when we add these two angles, we should get 180 degrees. So let's go ahead and measure those two angles to see if it works. So if we measure this angle here, we're getting 89. And let's measure the opposite angle to it. That's this one over here. Then we get 91. And 91 plus 89 is 180 degrees. So this shows that if you move it around, then you would get 180 degrees. That is, their sum would be 180 degrees. Now let's try to move it around and see what happens. So if we adjust the angle, and their sizes are changing, but you notice that it's still equal to 180 degrees. Now here we are up to 120. So 120 plus 60, still 180. And if we should take it around some more, 118 plus 62, still 180 degrees. So this demonstrates the idea that the opposite angles in a cyclic quadrilateral are supplementary. If we should measure these two angles, we would get the same idea, that is this angle here plus this one would actually give you 180 degrees. I'm going to get rid of this diagram and draw another one to demonstrate another part of the other part of the cyclic quadrilateral idea with the external angle formed. So let's start here, and I'm going to need a line to pass through because I want a diameter and I want to make sure that this is a diameter. So let's extend this and we get a diameter here. Now that I have my diameter, I'm going to draw a quadrilateral on my diameter. So here, that's 2, 3. Here's my quadrilateral. Put the final point there on the line. So now that I have my quadrilateral, I'm going to measure two angles that are opposite to each other. So this angle and this angle would be opposite to each other. So let's measure those two to see if they add up to 180 degrees. So here, 53. And if we should add this one here, sorry, if we should measure this one here, then whatever number we get should add to 53 to get 180. And as you see, 127 plus 53 does give you 180 degrees. So opposite angles here are supplementary, as they should be in a cyclic quadrilateral. Now, what about the idea of drawing an angle on the outside? So if we should draw this line, so we extend this line here and we get a point, sorry, put a point on it. And now we want to measure the angle that is formed on the outside. So let us measure that angle that is formed on the outside here and see what number we get. Well, it's telling us that it's 127, which is what we suspected, because the theorem says that the external angle formed is equal to the interior opposite angle. So this angle would be the same thing as that one. I'm gonna try it again, and to just extend this line and put a point on it so we can put an angle. So here we go. Let's measure this angle here on the outside. So this angle on the outside here measures approximately 114 degrees, which means that if we should measure this angle here, it should give us 114 degrees. Now let's try to measure it. So here we go. Right, and it tells us that it is 114 degrees. So the exterior angle that you draw is equal to the interior opposite angle, and opposite angles in a cyclic quadrilateral add to 180 degrees. And those are the two theorems that relate to cyclic quadrilaterals. Now let's jump back here and talk about the other stuff such as circles and tangents. Now, before we do that, let's answer these two questions. So angle B here, if we should find angle B, we know that these two angles are supplementary to each other. So we know that B plus 105 is equal to 180. And so we can say B is therefore equal to 180 minus 105. And so we get our size of our angle B to be 75 degrees there. Same thing here, A plus 86 gives you 180. And so we can subtract there, A is equal to, let me write a proper A. A would be equal to 180 minus 86. And from that, we have a 4 and 9. So 94 degrees would be the size of A. And in this case over here, we want to find C, remembering that the external angle formed, the external angle that you draw is equal to the interior opposite angle. So we don't have to work this out. We just know that C is equal to 101 degrees because that angle there is 101 degrees. And this other angle, like this one, if we should add them, then D plus 96 gives us 180. Just a reversal of this right here. So D would be equal to 180 minus 96. We do a subtraction there, and we get for the sides of our angle 74 degrees. So opposite angles in a cyclic quadrilateral are supplementary, and if you should extend this line and get an angle produced here, it's equal to the interior opposite. So that is that for cyclic quadrilaterals. Let's look at now circles and tangents. Now, a tangent, as you might recall, is a straight line that touches a curve at one single point. So when you draw a tangent to a circle, the radius that is drawn to the tangent at that point, we call it the point of tangency, fancy term, creates a right angle with that tangent. So the radius is perpendicular to the tangent at that point, creates right angles there. So that is always a case. So this is always something to remember because it comes up in those circle theorem questions. So this is one idea. I'm going to demonstrate them in a bit. The second idea is that if you should draw two tangents from the same point, so here we have a point A, and both the tangents AC and AB are drawn from that single point, then the both tangents will be equal to each other. So let's talk about this. These two tangents drawn from the same point, they are equal to each other. So this line is the same thing as that line. For that matter, these are radii, so they'll be equal to each other. And so what you get inside here is a shape, which is a parallelogram, which is a kite, and it has its own properties where this angle B plus, let's call this angle C here, would be equal to, when we add them together, we get 180 degrees. And because of the tangency, because of the right angles, this angle is a right angle, that angle is a right angle. And so what we get if we should split it down the middle are two right angle triangles in terms of one here and one there. And we can use those nice properties to solve our kind of angle questions. Now let's demonstrate this on the app and see what it looks like when we draw them. Let's clear this one. And so the first one we want to do is to put a tangent to a point. And so we're going to go to this section and say, all right, let me draw a segment. Here's our segment. This is our line segment. And now I want a line to be perpendicular to it, which is my tangent. All right, so here's my tangent, which is perpendicular to my radius. Now, the angle that is drawn here, as it says, whenever a tangent meets a radius, should be a right angle. So let me go ahead and measure that just to show that it's actually a right angle. So there it's telling you that it's a right angle, and on the other side as well, because once you have one right angle, there's always more than one. So at the point of tangency, the radius meets the tangent at right angles. Now let's look at the other idea, which talks about two tangents being drawn from the same external point. First, we need a circle, and here we go. Now I'm going to put another point on my circle because I need two tangents, and then let's put in the radius for each. So there's a radius, and here's a radius again. I'm going to bring this point over a little bit. All right, now I'm going to draw a tangent to this point. So let's put a tangent to that point by getting a perpendicular in there. So this will be our tangent here. Let's extend this. And let's put in another perpendicular here. And let's extend it as well. Now we have a common point here where these two tangents meet. Let me just put a point right there to mark it where they meet. And now what I'm going to do is measure these two lines. So I'm going to measure from here to here. And it tells me that that is 4.2. Measure from here to here. And it tells me that that is 4.2. So two tangents drawn from the same point will give you a will be equal to each other. That is very important. And if you should measure the angles that are formed now, remember that the tangent would meet the radius at a right angle. So that angle there would be 90 degrees. Also, if you should measure this angle and the angle here, then both of them should be supplementary to each other. That is, they should add together to give you 180 degrees, seeing that it's a kite. So here it says that that angle is 128. Let's measure the one at the other end here. 128 plus 52 gives you 180 degrees. So these two angles are supplementary, and these two angles are 90 degrees. And like I said, if you should draw this is a kite, and if you should bisect this line, then each of these angles would be, each of these triangles rather would be right angle triangles, and they carry their own properties as well that you can use to solve other questions. So two tangents drawn from the same point to a circle are equal, and the shape that they create with the radius is a kite. That is important. And then the final thing that we want to look at in terms of tangents and circles is the idea of the angle between the tangent and the chord. This should actually be chord, C-H-O-R-D, and there's a spelling there, C-H-O-R-D. So the angle between the tangent and the chord is equal to the angle drawn in the alternate segment. So this is your tangent, this is your chord. So here's a tangent, here's a chord. Let me just shade in that angle so that it becomes easier to view. So this angle that is drawn between the tangent and the chord is AB, would be equal to any angle that is drawn on this chord AE. So the angle drawn on this chord AE would be this angle here. And so you'd have that these two angles would be equal to each other because of that relationship. The angle drawn between the tangent and the chord is equal to the angle drawn on the chord. You could take it from the other side as well. So this is still a tangent and this is still a chord. So this angle that is drawn here between those two is equal to the angle drawn on the chord. And this chord AC, the angle drawn on it over here is angle CEA, and those two will be equal to each other as well. We're gonna go to the app and draw and demonstrate how it works. So let's head back over there and delete this so we can put in our diagram. Let's put in our circle. So here we go, here's our circle, and let's just leave it right there. Now we want to put in a tangent, so let's put in a tangent, and then we put in the chord. So all right, we want a tangent here. So let's extend this line and see how we can show that the angle between the tangent and the chord is equal to the angle drawn on the chord itself. So let us make a chord now. I'm gonna need a line for that. So let's take a line segment and start it here and end it here on the circle. So that's our line segment. So here we have an angle between the tangent and the chord. Now the idea is to draw an angle on this chord. So I'm going to use a triangle here to get an angle up there. So come on, attach. Nice. And then here's my triangle. So the angle that is drawn here between this chord and this tangent should be equal to the angle that is drawn on this chord itself, which is the angle up here. So let us do some measurement to see if it actually works. It does work, just to verify it. So measuring this angle here, we get 49 degrees, and then measuring this angle that is drawn between the tangent and the chord now should give us the same idea of 49 degrees. So they are equal to each other. The angle drawn between the tangent and the chord is equal to the angle drawn on the chord itself. These issues come up a lot in CXC questions, so you should at least play with it a little bit and get familiar with it. I'm recommending the app again. It's called Cabri Express. You can go to the Cabri website and download it for free and play around with this app and learn a lot of stuff from it. It's pretty much a geometry app. You can do a lot of things with it, constructions, etc. It's very, very nice for doing things like circle theorem, which is what I use it for. And if we want to measure this one over here, and then this angle that is drawn between this tangent and this chord, let's measure it. So we start there and we measure this angle here. It tells me that it's 64 degrees, and this 64 degrees, that is this angle on this side, should be equal to the angle that is drawn in here. Now let's measure that angle on that side of the triangle. And there you go. It says that it is 64. So the angle between the tangent and the chord is equal to the angle drawn on the chord itself. Notice again, here's your tangent, here's your chord. This is the angle between them, and the angle that is drawn on this chord, here it is, here are the two legs for the angle. They're both are drawn right here on this chord. So this angle here will be the same as the size of the angle up here. Both are equal to each other. And this one here will be equal to that one. So let's go back to our board. And here we see that when we draw the tangent and we draw the chord and both meet at that point, then the angle between here and here, the angle between the tangent and the chord is equal to the angle drawn on the chord. This is pretty much it. These are the other circle theorems. What is needed now is to practice these a lot. You can find questions at csecmathtutor.com by going into the practice paper section. There are loads and loads of questions in there that have to do with circle theorems. Getting there, some of them are simple CXE questions, so they are never just purely simple and straightforward. Some of them take a little bit of time to work out, but once you know the theorems and you have an understanding of how they work, then you can get through the diagrams by picking them apart. And remember that they're mixed with regular geometry, so you need to remember the regular geometry stuff. That's it for today. That's it for circle theorems. That's it for circles and tangents. Thanks for watching. And remember to go by csecmathtutor.com, get those papers on circle theorems and practice so that you can cement your learning and deepen your understanding. Thanks for watching.